Back in chapter 3, we had scatter plots. We talked about how to describe scatter plots, whether they were linear, nonlinear, unclear. We talked about direction, strength, things like that. Last section, we talked about how to run inference for regression lines. So how do we test whether there's a linear relationship between two variables, or how do we create a confidence interval to determine the true slope between two variables, and things of that nature. Now, what we're going to talk about today is what happens when we get a relationship between two variables that's nonlinear. So if we have two variables that come together and they have some sort of curve to them, we don't just get rid of those. Because even if they have a curve, there is some sort of relationship between those two variables in question. It's just not linear, which is what we use our regression model for. So what we're going to talk about today is how to take a nonlinear relationship and transform it. So using functions like taking a value squared, or taking the log of two sides, or whatever. So we're going to be applying functions to our data to get it to straighten out. So rather than having a curve, we have a straight line that then we can create a regression model for, and then we can use that regression model to predict or run tests to see if there's some sort of relationship. So the first type of model that we're going to talk about is called the power model. So this is just an example. Don't write this down. Okay? When you visit a pizza parlor, you order a pizza by its diameter. So 10 inches, 12 inches, 14 inches. Usually they just have small, medium, large, right? But what they're doing is they're basing it off of the diameter of the dough. Now, the amount of pizza that you actually get to eat is based on the area of the pizza, not based on the diameter. So the area of a circle is pi r squared. That's a formula you should remember from geometry. So the area of a round pizza with a given diameter, so with 10 inches, 12 inches, 14 inches, or whatever else might be going on for that particular company, is given by that formula. So area of the pizza is pi times the radius, which is just diameter divided by 2, squared. So what we notice, our final product, if we wanted to calculate the area of a pizza, we would take pi divided by 4 times the diameter squared. That would be our overall function. Now, when we receive a function in this form, where we have a coefficient times the variable x raised to some power. So in general, when we see a form of y equals ax to the p, that is known as a power model. So in our example here with the pizzas, our a value, our coefficient, pi over 4. The power we're raising x to is 2, so p. So when you get a model that has a power model, it's going to look like this form. Now, p can be any number. So it might be an integer like 1, 2, 3, 4, 5. It might also be a fraction, a rational, so like 1/2, which would be like the square root of x, or 1/3, the cube root of x, and so on. So p can really take on any value. So what you need to be able to do is, and this is where Algebra 2 comes into play pretty heavily here. In Algebra 2, you guys dealt with parent functions. So you knew the base form for an x squared, or you knew the base form for absolute value, or the base form for a logarithm, and things like that. So that's going to come into play here, because what's going to happen is you're going to start with your scatter plot. And based on that scatter plot, you got to think about, well, what type of model can I use? What does this look like so that I can apply the function and straighten the data out? That's going to be kind of the concept here. So with a power model, the basic form is some ax to a power. Now, when we have a model that follows this power model form, x and y definitely do not have a linear relationship. So what that means is if I were to make a graph of my x values compared to my y values. If I plug in a value for x, I get a value for y, and I plot those points. So if I do that, I'm going to get some type of graph that looks like this. Right? It's going to kind of curve up as we go. Or if p is a fraction, like a 1/2 or a 1/3, it would look something like this. Okay, so it's going to curve in the opposite direction. So this would be like an x squared curve. If I put in a value for x, my y values will get bigger by that squared value of x. So it's going to start curving up. Or if I have square root of x, like x to the 1/2, then as I go, my y values will level out as I go. So x to y is definitely nonlinear. It's going to have some type of curve to it. But if I take that same information and I apply the actual power to x. So if I apply a power to x, like x squared, or x to the 3rd, or x to the 4th, x to the 1/2, then in that case, my x to the p in relationship to y will be linear. So for instance, if I looked at my pizza problem here, if I just used x versus y, I'm going to get this parabolic shape. Because I have to take every x value and square it first, which means as my x values get larger, the y's are going to get larger by a squared value. Okay? So it's going to start curving up steeper and steeper and steeper there. But if I were to graph x squared versus y. So if I took all of my squared x values, so 1, 2, 4, 9, 16, 25, 36, and so on, those values will relate to y linearly. They will relate to each other in a linear fashion. So what's going to happen here in this section is we're going to be getting nonlinear scatter plots. And we're going to have to figure out what function to apply. Now, sometimes we'll apply the function to x. Like right here, we applied an x squared function. So every value of x we originally had, we're just squaring. So we take everything we had from our data and square all of our x values. Now when we compare that to y, rather than having a curve, we have a straight line like we want. That's the whole goal. It's apply a function to x, or apply a function to y, or apply a function to both that straightens out the model.
What Peter's talking, will it like have it in the equation, so like we use the area equation for this one?
Yeah, so it'd be things like, and it's something that like when you look at the variables, you might have an inkling like these should be related by a squared. Like here, if I'm talking area, x would be like a length. Well, length is one-dimensional, right? But area is two-dimensional. So we're probably going to raise it to the second power. Or if we had a linear relationship, so like a linear measure like length again, but we wanted to go to volume. Well, volume's a three-dimensional figure, so we would take x to the 3rd, right? So we do x cubed, and that should straighten out our model. Okay? Now, if you don't have any sort of inkling on what to do, you can always just kind of guess and check. You shouldn't have to do a lot of guessing and checking before you find a really good model. So you might try x squared first, and it might straighten it a little bit, so the curve's a little bit less. But then you'd be like, well, that doesn't quite work, so I'm going to go x cubed. And then x cubed might straighten it out, or you might say, well, I might need to go to x to the 4th, and so on. So you can just kind of keep trying until you find that spot that really gets you that linear model. Okay? But yes, a lot of times you should either be given the function to apply, or you guys should be able to think about which function should apply there. Okay? So, here's another example. So imagine you've been put in charge of organizing a fishing tournament in which prizes will be given to the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during your tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat. So what you then need is a way to convert length to weight. So if I know the length of the fish, what should the weight be? So instead of trying to get it still on a scale and trying to measure it in that manner, you could measure the length fairly easily and fairly accurately. And then if you had a relationship between length and weight, you'd be able to determine the weight based off of that. So you contact the nearby marine research laboratory. They provide reference data on length in centimeters versus weight in grams for Atlantic Ocean rockfish of several sizes. So they've given you the information you need. When a rockfish measured 5.2 centimeters in length, it weighed 2 grams. When it measured 8.5 centimeters in length, it weighed 8 grams, and so on. So what I want you guys to do in your calculators, I want you to input this data. And I want everyone doing this so you know the exact process that's going on as we go through this type of problem. So take a couple minutes, input that information. I don't have that many. So you might just want to look off of somebody as they do it. So here's what we need to do. Length, weight. Which one goes in list 1? Which one goes in list 2? Which one's the explanatory variable? Length. That's going to explain the weight, right? So length goes in list 1, weight goes in list 2. So I want you to put all of the values in. So this is one set of data, it just had to be in 2 rows to get it to fit on the screen. Take your time. Make sure you don't make any mistakes. Don't miss your decimal points. Don't mix the wrong numbers up. So get all of the lengths into list 1. Get all of the weights into list 2. Yeah, so both, that's just one set. I had to put them in 2 different rows just to get them to fit on the screen. So it's just one set of data there.
But the whole school votes combined.
Yeah. To get done before everyone else, make a scatter plot of the data.
Yeah, I have way more.
Because like, they're all lined up.
It's stopped at 20.
Yeah, the first one stopped at 20, the second one stopped at like.
Because you guys is the last one.
37.7.
Yeah, that's so weird.
Yeah.
Yeah.
Like, we just kept pressing enter, but it went to the second one, it's back to 20 now. No, mine's alright, mine stopped on, my first one stopped on 37.7.
Didn't clear the sentence.
Oh.
Did you guys wait to clear?
Same.
Yeah.
So delete those, delete the values from the list 2.
We're all like, what?
I did clear my split.
Oh, and you shouldn't have to re-enter. Don't, well, I guess if you cleared list 2, that's one thing, but if you had just done like, or whatever was in there initially, if you just hit delete, it'll just keep deleting those values until you get to the ones you want here. I was gonna say, no, they should match up exactly. So once you get that fixed, go ahead and create your scatter plot. No, order is very important. 5.2 has to go to 2, 8.5 has to go to 8.
Is that the first option?
Yes, it's the first option in your graph.
I accidentally deleted the first two and this three. Can I just point it out? And I'll delete this.
How many do you want? How do I do it? Yeah, it is. Say never been. What's the one market?
You said Aloha?
Zoom in. That's for everything. Zoom in always takes you to that section. Okay, so when you get your scatter plot, it should look something like this, right? Okay, so this would be one, if we were describing it, would be nonlinear, right? Now before, if we were trying to work with regression models, we would have just said, well, it's nonlinear, I can't fit a line, right? But now we're going to talk about a way to do it so that we can actually fit a line to this model and use that model to predict, use that model to run inference to see if there is a relationship between the variables, type of thing, okay? So when we look at this, we know it's curved, like so. So usually when it's curved, we could try a power model, okay? So we might try like an x squared or x cubed or x to the fourth, things like that, right? So if we think about this, length is a one-dimensional measurement. Weight would be three-dimensional it's like volume, okay? So weight is like a three-dimensional result or measurement. So what we need to do then is, or what we're going to try, is we're going to try taking every x value and raising it to the third power. Okay, now you can do that individually, so piece by piece. If you went in, so go to stat enter, or stat edit, sorry. Now don't start changing it yet. Just get into your lists. Now, from here, if you wanted to go one piece by one piece by one piece at a time, you could start with your 5.2 and raise it to the third. So you just type in 5.2 to the third, enter, and then go to the next one and cube it and enter. Now don't do that. Otherwise, you're going to be doing every single one at a time. Okay? So that's a way to do it. So if there's not very many items, it might not be that bad to just sit there and manually change them all to the new values, right? Another way to do this is to exit out. So exit out of your graph or your list. Now, we want to cube everything in list one, correct? So when you look at your number buttons, right above them you should see like list one, list two, list three, and so on, right? So if you hit second, and then the number that has list one on it, so I think that's 1. So go ahead and hit second 1. So now right now it's saying list 1. Now type in to the third. So you're going to hit second 1, then hit your caret key 3. Okay. Now for those of you with like the TI-84, make sure you hit the right arrow to get out of that exponent. So right now you should just see list 1 cubed. And now, when we take list 1 cubed, we need to store it so we save those values. If I just hit enter right now, it's just going to tell me what list 1 cubed looks like, right? But we want to keep those values. So we're going to hit the store key right above on. and then go ahead and store it in list 1. That way you don't have to keep changing your menus over and over and over again. So go ahead and hit second 1 again. So you're going to take list 1 cubed and replace the original list 1. So go ahead and hit enter. Now it's going to give you the results of what you have in list 1 cubed, right? So it just gives you that list there in the curly brackets. So if you go back into stat and edit, now you should see your new results. All of those values should have been cubed for you. Does everyone see that? Everyone good so far? Okay. Now, go ahead and exit out and create a scatter plot. So all you should have to do is go into stat plot, go ahead and hit zoom 9. Now make sure when you're making your scatter plot, make sure you're not doing a residual. Make sure you have list 1 and list 2 as your options. And now, when you graph it, what do you notice?
Almost.
Kind of wobbly.
Pretty much.
Yeah, it's a little bit wobbly, but for the most part, instead of having that curve to it, it looks like it's roughly linear, right? So rather than having a nonlinear relationship, by cubing every one of my x values, so now notice how my graph changes. Now my x-axis is length cubed. So what I'm graphing is x cubed versus y. So this first graph was an x versus y. The new graph that I created is x cubed versus y. Does everyone understand that? Okay. Now, what that means then is if I wanted to create a regression model for this linear relationship. So now, when I cubed my x values, I created a linear relationship. So, what we're going to do is we're going to go into our linreg function on our calculator. So go to stat, over to calculate. You're going to choose the linreg option and go ahead and evaluate. So if you chose the first option, your linreg should be y hat equals ax plus b, right? So what is the a value? What's your slope? 0.0146. And what's the y-intercept? So everyone agree with those values? Now, here's what we got to be careful with. When I create these on the calculator, what we're used to is just y compared to x. But this time, we're comparing y to x cubed. So when I write my equation, I'm going to say y hat is equal to, and if we write it in the way we normally write it with y-intercept first, so 4.066 plus 0.0146 times x cubed. I'm no longer relating x to y, so I'm not going to have something times x. It's got to be x cubed because that's what I did to all my x values. Does everyone understand that? So when you write your regression equations now, if you've applied some type of function to your x or to your y, you need to account for that in your regression line. So this is not an x to y direct relationship. It is a x cubed to y relationship. Is everyone okay with that idea? So in your calculator, it's still treating it as if x and y are together linearly, but you have to know that you applied a function, in this case to x, so you need to make sure you apply that function to x in your actual equation. Is everyone okay with that idea? Okay, so that's the type of thing we'll be working with most often there. And then from here, it might say, like, for this particular x value, what should your y value be? Now, originally, we wouldn't be able to do that because it was nonlinear. We wouldn't have applied a line to it. But now we can do that by plugging our x into this equation. So if they said I caught a fish that was 6.7 centimeters long, I can take 6.7 cubed times my slope plus my y-intercept, and I get my y-hat value, the weight of that particular fish. Okay?
Just like, how do you tell, like, since there's no, like,
Well, because right now, with this graph, there'd be no way to get a prediction value. So like the whole point of what of this process is, I want to be able to measure the fish on my boat and quickly calculate its weight without having to try to measure it while it's flopping around and I'm on a boat that's moving and I'm not going to get accurate weights. So I might throw a fish away that I thought was really light, but was actually pretty heavy. Okay? So what you want to be able to do is take a length, plug it quickly into an equation, and get the weight to know more accurately what it's looking like. So if I was starting with just length versus weight, I don't have a relationship I can predict with. But when I cube my lengths, now I have a linear model I can use to predict. So that's what we're using it for. It's saying, well, we had a nonlinear relationship, which means we have no way to predict. We're going to straighten it out. Now I have a way to use x and y to predict. Okay? Now, here's the other thing that happens. So maybe you didn't want to cube x, right? So in your calculators, we're going to undo what we did here. So we want to go back to our original x values. So if I cubed x to get where we are now, how would I undo that? Cube root. So what you're going to do is you're going to go find the cube root. So if you go into your math screen, it's like the 4th or 5th option down. Should just say cube root. So go ahead and hit that, select it. Now we want to cube root all of list 1. So now hit your second one. Hit the right arrow to get out of the radical. And then store in list 1. And hit enter. And now it should be back to normal. Everyone get that? So back to the original values. Now, if I cubed x to relate it to y, the other thing I could have done, since weight was a 3-dimensional object and I'm trying to compare it to a 1-dimensional object, instead of cubing x, I could have cube rooted y. So now I want you to do that. So cube root your list 2 now. So get your cube root, list 2, store it in list 2.
Do we store the cube root of list 1 in list 1? Is that what we're storing?
Yes, because you want to replace it with the original values. Okay, so you're good there. So now do the cube root of list 2 and store it in list 2. Okay, so now when you cube rooted all of your y values, go ahead and create your scatter plot. You should get pretty much the same looking graph. Now it's going to be a little bit different because you applied a function to different values. So one thing to note here is if you apply to y instead of x, you're going to get different values. But when I cube rooted the weight, notice I still got a fairly linear relationship, right? So real quick, run your linreg function. So I want to show you what happens to your line. So go ahead and run your linreg function. So now this time, what's our y-intercept? And then what's our slope? Okay? Now, notice that my y-intercept and my slope changed because I applied my function to different values. Okay? Now, when I write my equation, though, I need to look at how I related x and y. So this time, I left x exactly like it was. I left the length completely alone. Okay, so I'm going to leave it as x. So what did I do to y? I took the cube root, right? So I have a predicted value for the cube root of y. not until you get the actual value. So that's what you would do is when you solve, so you would now take a length. So you measure your fish and you get 6.7. Now when you put a 6.7 in for x, that's going to give you the cubed root of its weight. So then if you cube your resulting value, that gives you your new weight. So I mean, essentially, yes. But in our case, though, we have to leave it like this because we related x to the cube root of y. So we need to actually show how we transform. Does that make sense?
Why would you cube x but cube root y?
Because, so right here, we're going, this is one-dimensional. Length is just, it has one dimension to it, nothing else. Weight is three-dimensional. So we said we had to use that third power to relate the two. So I either need to take my one dimension and make it 3, which is why we cubed x, or I need to take my 3 dimensions and make it 1, which is why we would cube root.
So when the questions were asked, always minimal length and width?
No.
So then what the heck would you do then?
So, I mean, that's where you just have to kind of think about how would they relate. So and you can look at the picture itself, like this looks kind of parabolic. I mean, it looks like kind of like an x squared or an x cubed type of graph. So if you don't know off the top of your head, like here, this is one dimension, this is 3 dimension, we're going to do x cubed. We want to get those related, right? But if I don't know, if I have no idea how they would relate, I just know that it's curved, you can just kind of start guessing and checking. Like take all your x values and square. And if that straightens it out, perfect. You have your linear model, now you just go from there. Or if it doesn't straighten it out, then you go to x cubed and the next fourth and so on until you find what works.
What if there's something where it's like a 2-dimensional versus a 3-dimensional?
Then you'd have to use a fractional, like to the 2/3. Or to the 3/2 or something like that. I mean, to the 3/2, things like that. You probably won't have to do that, no. No, most of the time you'll be able to use the whole number. The only other ones that you might run into, like if this was curved this direction, this would be more like an x to the 1/2, so it would be a square root. So you would just take the square root of all of your x's, compare it to y, and go from there.
So, with, like, looking at the graphs, will they, the higher the powering go, will it just, like, curve more, or will they look like the actual, like, graphs, like, will it look like a hyperbola,
They should look like the graph that you would expect to see for like an x squared or for a whatever else. Like, and we're going to talk about some different types here. But yeah, it should look somewhat like you would expect the parent graph of that particular power to look. Yes. Okay. So that's a power model. Okay. And we just talked about 2 different ways to do it. So when you recognize a power model, it's just like a smooth curve. Okay. You can either raise x to the power that works the best. So you might not know off the top of your head what power to raise it to, so you just keep doing it until you catch the right power. Okay? So you raise the values of the explanatory variable and then relate those. So you're going to take x to the p and relate it to y. Plot those points. Or you can take the pth root of the response variable and relate it directly to x. So x can relate to the pth root of y. So you got 2 different options with that. Now, of the 2, I would generally choose option 1. It's a lot easier to work with when you just apply the power to x rather than trying to take a root of y. Okay? So instead of going x, y and plotting the points, we're going x to the p. Now, in those moments where you have to guess and check, so like if you tried x squared first, one thing you want to be very careful with is that if you took your list and squared it, before you go to check cubed, you want to undo what you did. So you need to go back to your original. So you want to square root the list first, then take the original cubed. And then if you want to undo that, and so on. So sometimes it can become a kind of tedious process.
Are you going to have to go much higher than the cube?
Not usually, no. And we're going to talk about even a different way to do this altogether that is sometimes easier just because it keeps things more consistent throughout, but these are the 2 that we talk about first. Okay? Now, with these power models, we can also use logarithms to relate x and y. Now, this is why I showed this one last, because as soon as I said logarithms, most of you guys, your faces just went down, your eyes rolled back in your head, and you're just like, I'm done. Okay? All right, so If we have a curved relationship that's related by a power model, okay, we can use logarithms on x and y to straighten out the model. Now this, the nice thing about this one, is I don't have to guess if it's squared or cubed or quartic or whatever, okay? All I have to do is take the log of x, take the log of y, and that should straighten it out fairly well. Now, again, when you're looking at this, you can use the base 10, so the normal everyday logarithm, so the one that on your calculator just says log, or you can use the natural log, that's that log as base e, and on your calculator would be that ln. So if you take your original information that's related by a power model, you take the log of x and take the log of y, then that should produce a linear pattern. So I'm not going to make you do this on the data we just had, but if you had your original two lists, you would do log of list 1 stored in list 1. Then you do log of list 2 stored in list 2. So now you've taken the log of both values, right? So then when you create your regression model, the only thing that would change is you have your predicted value for the log of y is equal to slope, or I'm sorry, y-intercept plus slope times log of x. So now instead of just having like an x cubed or a cubed root of y or something like that, you just have log of y and log of x. So you plug in your x value, find the side on here. Now, here's the question. If I take my x value, so I plug it in, so I take b plus whatever a is times log of x, right? That's going to give me some number c, we'll call it. Everyone understand what we're doing here? So I'm just saying we plug the value in for x, we get some value I'm just going to call c. If I want to find y, because the problem is I don't want log y, I want my actual y value. So if I use log base 10, how do I actually find y? How do I undo a logarithm? 10 raised to the other power. So I'd have my predicted value of y is equal to 10 to the c. To be honest, if I would use this probably anytime it worked. Like I would say, because like I said, you guys were asking like, well, how do I know when we square or cube or raise to the 4, things like that. With this, you don't have to worry. It should straighten it out fairly well enough that you can use this and just work from there. This is probably the easier of the two to actually transform. It's just you guys don't like working with logs as much, right? So that's why people tend to shy away from it. So if you don't absolutely know it's an x squared or know that it's an x cubed or something like that, this would probably be my choice because it's going to straighten it out and do the same thing.
So this would work with any network.
Any power model, yes. Any power model it should work with.
So since like all three different ways of doing this got its different values for A and B, is one of them like create a more accurate result for the predicted log?
Probably. And you won't know that because you don't know the true value, right? So basically what you would do is like if you don't feel like your transformation straightened it enough, you would want to try one of the other transformations. And maybe that straightens it more, and you just kind of keep working until you find one that you're comfortable with using. So yeah, depending on what one you choose, one's going to be probably more accurate than the other, but there's no way to determine that this is the most accurate one based on what you have. It's just you got to kind of go with what you have, okay? Now, along these same lines, we said you could use the base 10 log. If I do the same thing but with natural log, and here's the thing, this isn't going to matter which one you choose, log versus natural log. Okay, they'll both give you approximately the same thing. So in this case, once I put in my x value, I'm going to have my predicted natural log of y is equal to some constant c. But with natural log, my base is e. So when I want to find my predicted value for y, I would take e raised to the c value. Sometimes my e's and c's look very similar. So e raised to the c. Okay? So some of the things like in your homework, A lot of what I really want you guys to be able to get out of this is given an actual transformation. So a lot of your problems are going to tell you the transformation to use. I want you to be able to set up the equation and be able to solve for what's missing. So in essence, it's a lot of algebra. I'm only going through the background of all of this so you know where this is all coming from, right? So in the most parts, you're not going to have to worry about trying to find the exact value you want or the exact transformation you need. A lot of times they'll tell you that. You just have to be able to apply it and then solve. Everyone okay with that? All right. Now, the other thing that happens here, if log of both doesn't work, okay? A lot of times, especially if you get a graph that looks something like this, okay? If you get one like this and the log of both doesn't really straighten it out, it doesn't really get to where you want it to be, sometimes taking just the log of x will work as well. So you leave y completely alone, and instead of having x, you would do the log of x, and that should help straighten out the data. Okay, and that's one of the things. If you were working all the way from scratch, that you just kind of have to work with your lists until you get something that works. Okay, so like I said, we're not going to do a lot of problems like that because that could take forever. I mean, if you get in the wrong direction, checking different powers and things like that, you're going to take forever trying to find the actual value, right? So most of the time, I'll tell you kind of what you're working with. You just have to be able to apply it and solve for whatever we're looking for there. Okay? So, if you have a power model, you can try to find the exact power, or most often you can just take the log of both x and y, and that'll take care of everything. And then you just have log of y, log of x, and then you have to solve. It's just a little more involved process for solving the equation. Okay? All right. So we went through an example here where it kind of sees like this little power-looking model here. So if we take the log of both x and y, in this case it did natural log, it just takes that curve, straightens it out for us. Okay? So that's all that is. Another model. So the power model is one, an exponential model is another type. When you have an exponential model, so this is one, and these are pretty easy to spot because if you notice, they're going to climb really slowly at the very beginning, and then all of a sudden you're going to see this point where it just starts skyrocketing. Okay? So it kind of climbs, and then all of a sudden just shoots. So it's not this nice curve where it just kind of gradually becomes steeper and steeper, right? This would be a power model. When it really is kind of level at the beginning, it's just kind of gradually climbing, and then all of a sudden you see a point where it just starts to skyrocket. That's going to be an exponential model. So the one that they looked at in the book is the growth of the number of transistors that exist on a computer chip. So every time they create these computer chips, they have a certain number of transistors that help with processing power and things like that. So what they've noticed is that as they've progressed, the number of transistors they're able to fit onto one single computer chip has grown exponentially. Okay? So from 1970, so now this is years since 1970s are x variable. So when we get an x value of 10, that actually means 1980, right? So that's what you have to kind of think about running back and forth here. And then how many transistors they were able to fit on the actual chip. So like in 2010, they were able to fit over like 2 billion transistors onto one single chip. Okay? So, and as we progress, they're saying we should be able to continue exponentially there. So, in an exponential model, notice the difference here between the power and the exponential. The power model, our x variable was raised to an exponent, so x to the second, x to the third. In an exponential model, we have a number raised to the x. So now it'd be like 3 to the x, or 10 to the x. So x is actually in the exponent. So when that happens, when we have an exponential growth type of model, we need to look at relating x to the log of y. Now I chose to write natural log here. I tend to use natural log the most if it's just my choice. Otherwise you can use the regular log base 10. But when you have an exponential growth model, x related to the log of y will generally straighten out your relationship. So notice from that big steep curve that we had there, by just applying the natural log to the transistors to the y, we've straightened out our model fairly well. So an exponential type of problem, take the log of just y, and that should take care of everything you need there. Now, with that process then, and this is just more practice with what we've been doing, like when we have the regression equation, what does it look like and things like that. So in your homework, a lot of times they're going to give you the model to use, and then they're going to say, okay, here's your output, write the equation of your line. So give us the equation of your line to find variables. So for that example that we're looking at, the number of transistors we can fit on a chip, here's our computer output. Where do we find our slope and y-intercept? From the coefficients. Which one is the y-intercept? The top, 7.06. The constant's the y-intercept. The named variable is the slope. So note, since this was an exponential model, the equation, we took the natural log of y. So we have the predicted number of transistors, the natural log of the number of transistors is equal to y-intercept plus slope times years since 1970. So whatever model they chose to apply and whichever variable they chose to apply it to, you need to make sure your equation reflects that transformation. Okay? And then as far as any other types of problems you would see, you'd be like, okay, well, given that, how many transistors should we be able to see in 2020? So that just means plug 50 in for x. Now this 25 gives us the natural log of y. So then we raise it
students, please come to the front office.
and we get the number of
Asher
transistors.
Gillespie,
Okay?
Megan Helmberger, Haley Costello,
All right, so those are your problems. I want you to try out.
Larissa Heesler, Avery Cook, and Jaden Chauvinak. Please come to the front office.
Okay, on Monday, you'll have some time to work on this, but look at this stuff over the weekend. Don't go 2 days without it, or else you will forget everything. You have to start from scratch on Monday. Okay, so try out at least a couple of these this weekend.
I would just